We shall now switch over to deal with one of the most important and crucial portion of calculus, especially in applications of derivatives, called mean value theorems. These theorems have a wide range of applications in so many branches of mathematics, especially theory of equations and so many other branches also. First of all, let us understand what are mean value theorems. Actually speaking, there are so many mean value theorems called Darbach's mean value theorem, Rolle's mean value theorem, Lagrange's mean value theorem, Cauchy's mean value theorem, Taylor's mean value theorem, like that. Out of all of them, we take interest to deal with two of them in the beginning and remaining later. Those two are Rolle's mean value theorem and Lagrange's mean value theorem. The mean value theorem, rather the theorem which has brought a revolutionary effect in the theory of derivable functions. Yes, it has a wide range of applications. Almost all the mean value theorems which come after this are just nothing but applications of Rolle's mean value theorem. This is the historic background of Rolle's mean value theorem due to the famous mathematician Mr. Rolle. Of course, what is the actual statement? If f belongs to C of closed interval a to b, let us recall this symbolism. This represents the set of all functions which are continuous on closed interval a to b. F belongs to that means f is continuous on the closed interval a to b. Number 2. F belongs to D of open interval a to b. What does this symbol refer? C of means set of all continuous functions on closed interval a to b. D of open interval a to b means set of all derivable functions on open interval a to b. You please notice that here closed interval a to b is given in the data, but here it is open interval a to b only. That is, the hypothetical condition of Rolle's theorem need not require the derivability of the function at x equal to a and x equal to b. If at all f is derivable at x equal to a and x equal to b, we don't bother about it. We would have no objection at all. But actually it is not necessary. But it is a must that f must be derivable between a and b, that is at every point between a and b. And the third condition, which is the most important condition, f of a is equal to f of b. F of a is equal to f of b. The first point in the domain is a and the last point is b. F must be defined, of course, isn't it? It is a part of the domain. F of a must be equal to f of b. If at all there is any function which satisfies these three conditions, then there exists C belongs to open interval a to b such that f dash to C is equal to 0. My dear friends, it is not just enough if you can write these three conditions and the statement. It is not just enough. You may have to understand the essence very sincerely and clearly. Let us now do that. What is the importance of these three conditions? What are the important features of these three conditions? If any one of the conditions is omitted, what happens? What is the essence of the theorem? What actually he would like to say through this theorem? What is the geometrical interpretation of the theorem? In what way you can understand pictorially, that is graphically? What is the essence? What is the result? What is the usage? We shall now go to discuss with all those things. Again, let us recall what are the hypothetical conditions. There must be three conditions that must be satisfied. That is, f must be continuous on the closed interval a to b, f must be derivable on the open interval a to b, f of a is equal to f of b. Then at such a condition there is a c in the open interval a to b. Actually this word, this there exists, c belongs to open interval a to b. The existence of that particular word characterizes this theorem as the mean value theorem, such that f dash c is equal to 0. What do you mean by f dash c is equal to 0? We shall now see. Observe the graphs which are going to be given on the board. Observe the graphs of three different functions which have been given on the board. This is a smooth curve with no breaks, no cuts, no jerks. There is no point at which the sudden change of the direction of the propagation of the curve is observed. As it is a smooth curve, we believe that it is continuous. And it is possible to draw a tangent anywhere between these two endpoints. It is possible to draw a tangent, slope of the tangent exists. That is, it is derivable between a and b. Observe here also. Continuous, how? It's a smooth curve. Derivable, how? It's a smooth curve. Not only that, it is possible to draw a tangent anywhere between a and b. Yes. Observe the same thing here also. And in all these three diagrams, f of a is equal to f of b. F of a is equal to f of b. F of a is equal to f of b. These are the three hypothetical conditions of Rolle's mean value theorem. We could have just noticed, isn't it? What is the first condition? F must be continuous on the closed interval a to b. So on the closed interval a to b, in all these three graphs, they represent a smooth curve. Therefore, continuity is okay on the closed interval a to b. And now about derivability. Because of the smoothness, it is possible to draw a tangent at any point between a and b. Therefore, f dash x is this. That is, f is derivable on open interval a to b. You see, we do not require f dash a and f dash b here. You see? Okay. The third condition, f of a is equal to f of b. Then, what is the conclusive part of Rolle's mean value theorem? So far, we could have discussed the hypothetical conditions only. The three conditions we could have demonstrated, rather we could have represented in these three graphs. What is the conclusion? Read out. There is one C. There is at least one C. There exists C means there is at least one C, such that f dash to C is equal to 0. Well, my dear friends, what is f dash to C? Slope of the tangent at x is equal to c. F dash is equal to 0 means slope of the tangent at x is equal to c is 0. Come on, you recollect. What are all those lines whose slope is 0? Those lines which are parallel to x-axis, isn't it? That is, by saying that f dash c is equal to 0, we believe that slope of the tangent at x is equal to c is 0. That is, the tangent at x is equal to c is parallel to x-axis, because slope of x-axis is 0. Two lines are parallel when and only when the slopes are equal. Slope of x-axis is 0 and f dash is c is equal to 0. That is, slope of the tangent at x is equal to c is 0. Therefore, the tangent at x is equal to c is parallel to x-axis. Come on, observe. That is the point C at which the tangent on the curve at x is equal to C is parallel to x-axis. Parallel to x-axis. Well, what is C here in this diagram? What do you say about the tangent at x equal to C? Surely it is parallel to x-axis. Here is only one C. There only one C. Observe here. Tangent at this point parallel to x-axis. Parallel to x-axis. Parallel to x-axis. C1, C2, C3. We are able to observe three different values for C at which the tangents are parallel to x-axis. Therefore, in order to explain the statement of Rolle's theorem geometrically, simply by looking at these diagrams, it can be said like this. If at all there is a smooth curve defined on the closed interval A to B which is continuous, of course, underiable, with f of A is equal to f of B, then it is possible to draw at least one tangent parallel to x-axis on the curve. It is possible to draw at least one tangent to the curve parallel to x-axis. Here we are able to draw only one tangent parallel to x-axis. Here we are able to draw only one tangent parallel to x-axis. Here in this curve we are able to draw three different tangents to the curve parallel to x-axis. Depending on the nature of the curve, there may exist so many C's. We do not bother, but there must exist at least one C belong to the open interval A to B. Well, this is about Rolle's theorem. What is the importance of the three conditions given? If the first condition is lapsed, that is, if f is not continuous on the closed interval A to B, then what happens? Like here. Continuity is missing. Where can you draw a tangent to the parallel to x-axis? In this portion, function is not continuous. It's not a smooth curve. It is not possible to draw a tangent parallel to x-axis. So, out of the three conditions of Rolle's mean value theorem, hypothetical conditions of Rolle's mean value theorem, the first condition, no doubt it must be necessary. Okay, second one. If the second condition fails, that is f is not derivable, then it is a must. It must be provided. Unless or otherwise, it is just meaningless at all to speak of f dash c, isn't it? Unless f is derivable in open interval A to B, how can you say that there is one c with f dash c is equal to 0? Not possible at all. So it is a must. Second condition is also a must. What about the third condition? What happens? Is it a sin if f of is equal to f of is not given? Let us see. Observe the graphs. It is a smooth curve. No doubt. So continuous. Understood. Derivable also in the open interval A to B. I am not speaking of the derivative at B. But you see, f of A is longer, f of B is shorter, f of A is not equal to f of B. You see, it's not equal. They're not equal. Come on, friends, where can you draw a tangent parallel to x-axis? Where can you draw? On the curve. You're supposed to draw a tangent parallel to x-axis. Is it possible? So no such tangent will be parallel to x-axis. There will be no tangent whose slope is 0. That is, there exists no c with f dash is equal to 0. So, Rolle's theorem failed because of the third condition. Someone can say that you observe this graph. Okay, sir, this is a smooth curve. F of A is not equal to f of B. F is continuous on closed interval A to B. F is derivable on open interval A to B. And f of A is not equal to f of B. The third hypothetical condition of Rolle's mean value theorem is failed here, of course. Even then, we are able to draw a tangent parallel to x-axis here. That is, there is one c with f dash c is equal to 0. For this function, it is okay. For this function, it is not okay. Therefore, it is not a general condition. It is not valid for any type of such functions. Not valid. That is, we cannot generalize this. Sometimes it might be correct, sometimes it might be false. Therefore, in order to state it as a theorem, one must give that f of A is equal to f of B. Unless or otherwise, it is just not possible to say that there is one c with f dash c is equal to 0. That is, slope of the tangent is 0 at least one of the points, say c, between A and B. You can observe direct evidence. Here you cannot draw a tangent parallel to x-axis, you see. Therefore, third condition is a must. Well, my dear, such discussion, is it necessary for us? Absolutely necessary. Why? Because we must be able to recollect the conditions of Rolle's mean value theorem. We must be able to reuse the statement again and again. To understand it perfectly, we could have discussed with all these things. This is what that Rolle's theorem says. Now, let us observe some famous applications of Rolle's mean value theorem. Consider the function on closed interval 0 to 2 pi. Everybody knows that this is a continuous on closed interval 0 to 2 pi and derivable in the interval open interval 0 to 2 pi. Well, what is f of 0? Sine 0. What is f of 2 pi? Sine 2 pi is 0. So, therefore, the first condition, what is the first condition? F is continuous on closed interval A to B. Second condition? F is derivable on open interval 0 to 2 pi. Third condition? F of A is equal to 0 is equal to f of 2 pi. F of A is equal to f of B. The third condition is also satisfied. Therefore, all the conditions of hypothesis of Rolle's mean value theorem have been satisfied. Hence, we can apply Rolle's mean value theorem for this function, by applying which we see that f dash, there is one c such that f dash to c is equal to 0 for some c belonging to. By the by, what is f dash c? f of x is equal to sin x, f dash x is equal to cos x, f dash c is equal to cos c. That is, cos c is equal to 0 for c belongs to etc. etc. Well, my dear, when can cos c be 0 between open interval 0 to 2 pi? C is equal to pi by 2, 3 pi by 2. Any more? No more. Therefore, for f of x equal to sin x, it is possible to draw a tangent at two different points which are parallel to x-axis, and it can be observed in the graph also. One can easily see that there are two tangents parallel to x-axis drawn on the curve y is equal to sin x in between 0 and 2 pi. This is pi by 2 and that is 3 pi by 2. You see, the tangent drawn at x equal to pi by 2 is parallel to x-axis, and the tangent drawn at x equal to 3 pi by 2 is also parallel to x-axis. So this is the direct application of Rolle's mean value theorem. Well, if I change the domain like this, can you apply Rolle's mean value theorem for f of x equal to sin x now? Between pi by 2 and pi. Clearly f of x equal to sin x, continuous. F of x equal to sin x is derivable also. First two conditions of Rolle's mean value theorem are clearly satisfied. What do you say about the third condition? What is f of pi by 2? Sin pi by 2 is 1. What is f of pi? Sin pi is 0. F of a is 1 and f of b is 0. So f of a is equal to f of b is not being satisfied here. We strictly say that Rolle's theorem cannot be applied to f of x equal to sin x on pi by 2 to pi. Cannot be applied. There may exist or may not exist. We are not sure of the existence of c between that is in the open interval pi by 2 to pi. It's very clear, of course, by looking at the graph. That is f of x equal to sin x in the interval pi by 2 to pi. Where can you draw? Where can you draw a tangent parallel to x-axis on the curve y is equal to sin x? It is just not possible. And that has been noticed by Rolle's theorem itself in the beginning. As f of pi by 2 is not equal to f of pi, we cannot apply Rolle's mean value theorem for that function. Okay. F of x is equal to cos x on closed interval 0 to 2 pi. Can you apply Rolle's mean value theorem or not? Come on, observe. F of x equal to cos x is of course everywhere continuous and everywhere derivable, no problem. What is f of 0 and f of 2 pi? F of 0 is cos 0 is 1. F of 2 pi again 1, isn't it? At 2 pi is also 1. Observe the graph. f of 0, 1. f of 2 pi, 1. So Rolle's theorem can be applied because we could have seen almost all the three conditions. First condition is f is continuous, that is cos x is continuous in the closed interval 0 to 2 pi. Second condition is f is derivable, that is f of x equal to cos x is derivable in the open interval 0 to 2 pi. And the third condition is f of 0 is 1 and f of 2 pi is also 1. It's very clear from the graph itself, or else everybody knows about the nature of the cos function, no problem at all. So f of 0 is equal to 1 and f of 2 pi is also 1. And the third condition is also verified. Good. Therefore, it is possible to draw a tangent parallel to x-axis on the curve. Where is it possible? Of course, here it is possible. So, at the point pi it is possible, and you see we could have grasped it by looking at the graph. Is it true? Let us now gather the theoretical evidence about that. It is continuous, it is derivable, f of 0 is equal to f of 2 pi. Therefore, there is one c, there exists one c such that f dash to c is equal to 0 for some c belongs to open interval 0 to 2 pi. What is f dash c? Minus sin c, isn't it? F of x is equal to cos x. F dash x is equal to minus sin x. F dash to c is equal to minus sin c. Minus sin c is equal to 0. Sin c is equal to 0 from some c, for some c in the open interval 0 to 2 pi. Well, my dear friends, when can you say that sin x is equal to 0? Sin x becomes 0 when x is n pi. That is 0 pi, 1 pi, 2 pi, 3 pi, 4 pi and so on. But you see, we must have the answer between 0 and 2 pi, and it is only 1, that is 1 pi. What is that? Pi. Here, in the case of cos x, on the closed interval 0 to 2 pi, we could have had only one c, whereas in the case of f of x equal to sin x, we could have had two values for c of Rolle's mean value theorem. Moreover, if I change the function from 0 to pi, can you apply Rolle's mean value theorem? If I change the function, that is, if I change the domain of the function to 0 to pi only, look at the graph. Is it possible to draw a tangent parallel to x-axis? At 0, it is at 1. At pi, it is at minus 1. Where can you draw the tangent parallel to x-axis? It can easily be understood that it is not possible to have such a tangent parallel to x-axis. And that can be said with the theoretical evidence also. Why? Because f is continuous, that is cos x is continuous. First condition of Rolle's mean value theorem is satisfied. Cos x is derivable. Second condition is also satisfied. But the third condition, that is f of a is equal to f of b, fails here. Why? Because f of 0 is cos 0, 1. F of pi is cos pi minus 1. They are not equal. F of a is equal to f of b is failed. So we cannot apply RMVT, that is Rolle's mean value theorem cannot be applied. Of course, at this juncture, we cannot find c between 0 and pi such that f dash c is equal to 0. That is equivalent to say that it is not possible to draw a tangent on the curve at a point on the curve which is parallel to x-axis. This is the wonderful and powerful, the most powerful concept in differentiation, that is about mean value theorems. Well, there is one more standard function which must be kept in mind. which must be kept in mind. We shall be looking at that. Let us now observe the function. F of x is equal to x minus a whole to the power of m into b minus x whole to the power of n for all x belongs to closed interval a to b, where a and b are two real numbers with a less than b. Observe the function very carefully. No doubt it is a polynomial in x of degree m plus n. And we know that every polynomial function is both continuous and derivable on closed interval a to b. Of course, we need to have the derivability on open interval a to b enough. But here it is derivable on closed interval a to b also. And what about the third condition? What is the third condition? F of a. What is f of a? A minus a 0, 0 into everything is 0. So f of a is 0. What about f of b? What about f of b? B minus b is 0 and 0 and anything is 0. So again f of a is equal to 0 is equal to f of b. We can apply Rolle's mean value theorem. You see, the importance is not the question of testing whether Rolle's theorem can be applied or not. The major importance lies with the C, the point C of Rolle's mean value theorem. That must be remembered here. How can we keep that in mind? Let us see. First of all, what is that? F belongs to C of closed interval a to b. Why? Is it a polynomial of m plus nth degree? No doubt it is continuous. And with the same argument, we say that f belongs to D of open interval a to b also, it is derivable on open interval a to b. And f of a is equal to f of a is equal to 0 and f of b is equal to 0. Therefore, both are equal. F of a is equal to f of b. These three steps say to us that F satisfies all the conditions of hypothesis of Rolle's mean value theorem. And by Rolle's mean value theorem, I would like to abbreviate Rolle's mean value theorem by RMVT. F dash is equal to 0 for some C belong to open interval a to b. So we could have concluded. Now it is our responsibility, of course, to know C. What will be the nature of C? How can you pick out that C? How can you remember that C? That is the thing before us to perform. Well, what is F dash next? U, V, product rule we are supposed to use. U derivative into V plus V derivative. Because derivative of B minus X is for B it is 0 and for minus X it is minus 1, so it is minus 1. V dash into U. This is M into minus N into is equal to x minus whole power m into b minus x whole power n. You can get it out. That is f of x into m by x minus a minus n by b minus x. This is f dash x. This is f dash x. Okay, but you see, we should have f dash c is equal to 0. Yeah? F dash c is equal to 0 for some c belongs to open interval a to b. That is, but f dash c is equal to 0 for c belongs to open interval a to b. C belongs to open interval a to b means c is different from a and b. C is not equal to a. So, c minus c not equal to 0. C is different from b. B minus c not equal to 0. So, f of c not equal to 0. Implies f dash to c is equal to 0 and f of c not equal to 0. You see, this is f dash x. We are to use these two conditions. Well, for the sake of calculation purposes, I would like to remove these two steps, of course, just to save some space on the board. Okay, f dash c is equal to 0 means m by c minus a minus n by b minus c is equal to 0. Why? Because f of c not equal to 0, the product is 0. As this is not 0, this must be 0. That is m by c minus a minus n by b minus c is equal to 0. That is, m by c minus a is equal to n by b minus c. Cross multiply. mb minus mc is equal to nc minus na. Or mb plus na is equal to m plus n into c. Or c is equal to mb plus na by m plus n. C is equal to mb plus na by m plus n. That you must remember. What is m? The exponent given to x minus a whole power m. What is a? The smaller value between a and b. A is less than b. The a is smaller and b is bigger. What is n? Exponent that must be given to b minus x whole power n, isn't it? So that mb plus na by m plus n. Of course, this C is the point on x-axis which divides the segment joining A0 and B0 in the ratio m is to n internally. It can easily be understood, isn't it? mb plus na by m plus n. By using the section formula, you can easily notice that the point C is the point on x-axis which divides the segment joining A0 and B0 in the ratio m is to n internally. Yes, that is nothing but C. That is having much and of course great importance. How? How can it be reused again? We shall see. What is C here? F of x equal to x minus 3 whole to the power of 5 into 4 minus x whole to the power of whole cube, where all x belongs to closed interval 3 to 4. And one can easily say that Rolle's theorem can be applied to this function. What is C? mb plus na m plus n. It is 8. And you can easily observe 29 by 8 is greater than 3 and less than 4, isn't it? What is 29 by 8? It is 3 point something, isn't it? It lies between 24 by 8 and 32 by 8. Hence, it lies between 3 and 4. So, C belongs to open interval 3 to 4. Like this, you can be able to estimate the value of C directly by looking at that as a formula, as a standard result. That result which can be reused again and again must be kept in mind That is nothing but called a formula. That is nothing but called a formula because the reusability is more for that result. That is why we say that it is a formula. Well, let me give you one more question. Let me create one more question, of course, which was given previously. Yes, let us look at that. Observe the question. F of x is equal to x minus 1 whole cube into 3 minus x whole to the power of 4 where x belongs to closed interval 1 to 3. If f dash c is equal to 0 for some c belongs to open interval 1 to 3 and c is equal to p by q, what is the value of p minus q? The question looks very longer and bulkier. But you see, once you remember the standard result C is equal to MB plus NA by M plus N, then it becomes so simple. It can be answered within fraction of a minute or a second even. Yes. How? First of all, what is C? One thing is very clear. It is a polynomial of 7th degree. It is both continuous and derivable. Moreover, f of 1 is 0 and f of 3 is 0. So, Rolle's theorem can easily be applied without any hesitation, no problem at all. So that C, what is C? C is equal to MB plus NA. 3 3s are 9 plus 4 1s are 4 by 3 plus 4 7. That is 13 by 7. And it is direct to say that P is 13 and Q is 7. But what is the question asked here? What is the value of P minus Q? That is 13 minus 7. Answer is 6. You think of, my dear, why the process of answering has become so simple? Simply because you could have reused the previous result. That is C is equal to MB plus NA by M plus N. MB plus NA by M plus N. That is the greatness of that result, the reusability of this result again and again we are able to see. As so the answer for this question is 13 minus 7, that is 6. Is 6. You see, in whatever fashion he may ask you, you must be knowing P and Q, and you can know. It's not impossible, it's very easy. This is simply because of the application of Rolle's theorem, isn't it? Good. Next, let us look at one more application of Rolle's mean value theorem in the theory of equations. Another multiple choice question, of course having only one answer. Observe the question very carefully. It has been given that a plus b plus c is 0. Then 3ax square plus 2bx plus c is equal to 0 has at least one real root in. An application of Rolle's theorem. What do you have from Rolle's mean value theorem? F dash c is equal to 0. That is, f dash x is equal to 0 has a root in open interval a to b. That you must understand. What is the essence of Rolle's mean value theorem? F dash c is equal to 0 for some c in open interval a to b. What does it mean? F dash x is equal to 0 has a root. Okay, therefore you must consider, you are supposed to consider this as f of x or f dash x? F dash x. Yes. Now, that type of thinking is essential here in applying Rolle's mean value theorem or in making an attack on the problems regarding Rolle's mean value theorem. Well, come on, give me an idea. What can you define f of x? In what way should we define f of x? One thing he has given, a plus b plus c is equal to 0. So f of 1 is 0. What is f of 0? 0, 0, 0. So I like to define this function on closed interval 0 to 1 Yes, of course. Closed interval 0 to 1. Simply because I must be able to use the data given. He has given us a plus b plus c is equal to 0. I may have to use it. That is, I have to define f of x such that a plus b plus c is equal to 0 is to be encashed. That is why I have defined f of x on that closed interval 0 to 1. Now you look at it is a third degree polynomial, no doubt about it. It is continuous on closed interval 0 to 1. And simply because of the same reason, the f is derivable on open interval 0 to 1 also. Therefore, f dash c is equal, moreover, f of 0, 0, f of 1, 0. Isn't it? Clearly. F belongs to C of closed interval 0 to 1. F belongs to D of open interval 0 to 1. F of 1 is equal to 0 is equal to f of 0. Because a plus b plus c is 0, f of 1 is nothing but a plus b plus c. You see, it is 0 from data. Therefore, from these three conditions, we notice that f satisfies all the conditions of hypothesis of Rolle's mean value theorem. All the conditions of hypothesis of Rolle's mean value theorem. Therefore, f dash c is equal to 0 for some c belongs to open interval 0 to 1. F dash c is equal to 0. That is, f dash x is equal to 0 has a root in open interval 0 to 1. What is f dash x? 3x square plus 2bx plus c is equal to 0. Hence, this must be the right answer. That must be the right answer. Like this, we have so many applications, a wide range of applications of Rolle's mean value theorem, and there is no end at all. We have to put a comma but not a full stop. Okay. So there is a time factor before us.